Welcome students to another lesson, lesson 47. In this lesson, we will discuss width of central and secondary maxima. So the question states, deduce the expression for the angular width of central maximum. So the angular width of central maximum is the angular separation between the direction or angle of the first minima on the two sides of the central maximum. Now what does this mean? If this is my first minima, then the direction or the angle, this is my angle for the first minima. So the angular width will be the angle of the minima on both the sides. So here is one minima and here is another minima. Total angle, this total angle is known as your angular width. So if this is your total angle or this is your angular width, then this will be your half angular width. What is half angular width? The direction of the first minima on the either side of the central maximum, and it's given by theta equals to lambda by small d. Lambda is the wavelength, d is the slit width. Next, your angular width of the central maximum is twice of this angle, just like we have seen. So this is twice theta equals to twice of lambda by small d. Moving to our next question. Deduce the expression for the linear width of the central maximum. Now, suppose this is my central maximum and d is the distance of the screen from the slit, then by using this formula, angle equals to arc upon radius. In our case, this is my angle twice of theta. So angle equals to arc upon radius. In this case, our arc is this one. Now note the distance of this arc and this distance, which is beta naught. They are not quite, or they are quite similar. There's not much difference between the distance of this to one. So I can consider this line as my arc. And how much is the length of this line? Beta naught. So my angle equals to arc, which is beta naught divided by the radius. So this is the radius, and how much is this distance? Capital D. So twice of theta equals to beta naught by capital D. Now I can send this d to the other side. So I can write my beta naught as d times of twice of theta. So this beta naught is my linear width. Therefore, this beta naught can be written as beta naught equals to d times twice of theta. And what is your theta? Theta is the half angular width, and we have derived your half angular width. How much is that? Lambda by small d. So beta naught, or your linear width, can be written as beta naught equals to twice of d lambda by small d. This is my linear width. Moving to our next question. Deduce the expression for the linear width of the secondary maxima. So to find out the expression for the linear width, just like in our previous case, first we have to find out the angular width of the nth secondary maxima. That means any secondary maxima, whether it be your first secondary maxima, second secondary maxima, third secondary maxima. So I have said nth secondary maxima. The angular width of this nth secondary maxima is the angular separation between the nth and the n plus 1th minima. If this is my nth minima, then the direction of the nth minima, or I can say the angle of the nth minima, is theta n equals to n lambda by d. Now the succeeding minimum will be direction of the n plus 1th minimum will be theta n plus 1 equals to n plus 1 lambda by small d. So if I can find out the direction of the nth minimum and the direction of the n plus 1th minimum, suppose if I can find out this direction of the nth minimum and direction of the nth minimum and the direction of the n plus 1 minimum, then I can find out this angular separation by subtracting the value of the nth minimum from n plus 1 minimum. Therefore, angular width of the nth secondary maximum equals to theta n plus 1 minus theta n plus 1 lambda by d minus n lambda by d, and this n lambda by d will get cancelled. So what will I be left with? Lambda by d. So the angular width of the secondary maximum is how much? Lambda by d. Or I can. So if my angular width is lambda by d, so the lead of the nth secondary maxima will be angular width times capital D, just like in our previous case. So angular width is lambda by small d, then my linear width beta d times lambda by small d. Now note, the linear width of the secondary maximum which we have derived was beta naught equals to twice of d lambda by d. Now, do you notice? Yes. So clearly the width of the secondary maxima is twice the width of the secondary maxima, or I'll say the width of the central maxima is twice the width of the secondary maxima. Thus, the central width of the diffraction pattern is twice as wide as the secondary maxima. Now, what does this mean? Suppose you have this. If this is my central bright fringe and this is the length of this bright fringe, then my secondary bright fringe will be half of this central bright fringe. Fine. So this is an important point. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So thank you.